Hey guys, welcome to this explainer. Look, if you are deep in the middle of your university CS exam crunch right now, you are in exactly the right place. Today, we're doing a rapid, high-yield masterclass covering 9 absolutely essential calculus topics. We're going to cover 3 methods for limits, 4 methods for derivatives, we'll do a deep dive into integration and partial fractions, and finally tackle 3 exam-style scenario questions. Our goal is simple, right? Maximize your understanding and maximize those marks. Okay, let's dive right into this. So here's the game plan for today. 1. Limits and core methods. 2. Derivative techniques. 3. Integration concepts. 4. Applied scenarios. And 5. Advanced L'Hopital's rule. Let's get to work.
Module 1, Limits, Core Evaluation Methods. We're going to master 0 over 0 and infinity over infinity forms.
Okay, our first technique is factorization. Now, the trigger for this is pretty straightforward. You use it when direct substitution gives you a 0 over 0, and your expression is a polynomial that can clearly be factored. The steps are super quick. Step 1, substitute to verify you actually have that 0 over 0 form. Step 2, factor both the numerator and the denominator. And step 3, just cancel out that common term and substitute your limiting value one more time. Let's actually see this in action. Take this limit as x approaches 3. Plugging in our 3 straight away gives us an indeterminate form, so we factor. The numerator is a classic difference of squares. We instantly see the x minus 3 terms cancel out perfectly, which leaves us with just x plus 3. Substitute the 3 back in, and boom, we get 6. Quick and clean. All right, moving on to method number 2, rationalization. You're going to trigger this maneuver when your expression contains a square root, and direct substitution still gives you that 0 over 0 form. The real trick here is to multiply both the numerator and the denominator by the conjugate of the radical term. What this does is create a difference of squares that cleanly removes the root, allowing you to easily cancel and substitute. For example, we want the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. Plugging in 0 straight up gives us 0 over 0. So we multiply the top and bottom by the conjugate, the square root of x plus 1 plus 1. On the top, the difference of squares simplifies beautifully to just x plus 1 minus 1, leaving us with exactly x. Now that x on top cancels right out with the x on the bottom. We're left with 1 over the square root of x plus 1 plus 1. Plug in x equals 0, and our final answer gracefully settles at 1 over 2. Next up, the absolute powerhouse, basic L'Hopital's rule. Now, the absolutely crucial point here, and examiners really love to test if you remember this, is step 1. You must confirm the form is exactly 0 over 0 or infinity over infinity. Seriously, L'Hopital does not apply otherwise. Once you've confirmed that, you differentiate the numerator and the denominator completely separately. Do not use the quotient rule here. Then you just reevaluate. Look, sometimes mechanical persistence pays off. Check out this limit as x approaches 0 for e to the power of x minus 1 minus x all over x squared. Direct substitution gives 0 over 0, so we apply L'Hopital once. The derivative of the top is e to the x minus 1. The bottom becomes 2x. But wait, plug in 0 again, and we still get 0 over 0. Don't panic, just do it again. The second derivative of the top is simply e to the x. The bottom is just 2. Now plug in 0. E to the 0 is 1, so our final answer is 1 over 2. Okay, Module 2, Derivatives, 4 essential techniques. We're looking at first principles, standard rules, implicit, and parametric. We're kicking this off with first principles, or the ab initio definition. The formula is the limit as h approaches 0 of f of x plus h minus f of x all over h. If we differentiate sine 2x, our numerator becomes sine of 2x plus 2h minus sine 2x. To actually solve this, you need the sum to product trigonometric identity, which gives us 2 times cosine of 2x plus h times sine of h. When we divide by h, we group the sine h over h together, and as h approaches 0, sine h over h famously approaches 1. This leaves us with our final derivative, 2 cosine 2x. Moving right along to standard rules, let's look at the product rule. Think of this as a quick mechanical refresher for those high-stress exam moments. Say we have y equals x squared times secant 4x. The rule is simply the first times the derivative of the second plus the second times the derivative of the first. That gives us x squared multiplied by the derivative of secant 4x plus secant 4x multiplied by the derivative of x squared. Grouping these terms cleanly together gives us 2x secant 4x plus 4x squared secant 4x tangent 4x. Now, what about implicit differentiation? That's used when your x and y are all tangled together. Take y equals x cosine y.
We differentiate both sides with respect to x. The left side simply becomes dy by dx. On the right, we use the product rule. The first is x. The derivative of cosine y is negative sine y times dy by dx, plus the second, cosine y, times the derivative of x, which is just 1. Next, use a little algebra to gather all your dy by dx terms on one side, factor it out, and you cleanly isolate dy by dx to get cosine y divided by 1 plus x sine y. And to finish our derivative medley, we have parametric equations, where x and y are defined by a third variable, t. We find dy by dx by calculating dy by dt and dividing it by dx by dt. Given our equations here, dx by dt simplifies to a times cosine t minus sine t. Differentiating y requires a quick product rule for that t cosine t term, which beautifully simplifies dy by dt down to just a times t sine t. Divide the y derivative by the x derivative, those a's cancel right out, leaving us with t sine t over cosine t minus sine t.
All right, take a quick breath. Module 3, Integration Concepts and Fractions. We're breaking down by parts, the e to the x trick, and partial fractions. Here are two absolutely fantastic techniques. First, integration by parts for x sine x. We set u equal to x and dv equal to sine x dx. Applying the formula u times v minus the integral of v du, we get negative x cosine x plus sine x plus c. Then there is a massive time saver you need to know, the e to the x trick. The rule states that the integral of e to the x times the sum of f of x and its derivative f prime of x is quite simply e to the x times f of x. So for the integral of e to the x times x plus 1, notice that if f of x is x, its derivative is exactly 1. It perfectly matches the form. The answer is instantly e to the x times x plus c. Oh, and a quick tip for your exams, make sure you memorize the standard reduction result for e to the ax sine bx because it is super common for those prove that questions.
Now for a real heavy-hitting tool for those high-value exam questions, partial fraction integration. The method involves 4 distinct steps. First, factor the denominator completely. Second, set up your partial fraction form and pay special attention to repeated factors because those need incrementing powers. Third, multiply through and plug in your roots to solve for your constants a, b, c, and so on. And finally, step 4, integrate those newly separated, much simpler terms. Let's look at this absolute beast of an equation. Our denominator has a distinct root and a repeated cubic root, which dictates our specific partial fraction setup. By multiplying through and plugging in our x values, the constants a and d reveal themselves almost instantly. Matching up the coefficients gives us the rest of them. Integrating the resulting, much simpler sequence term by term yields our final result. I'll just give you a second to let that full breakdown on the screen sink in. Module 4, Applied Scenarios and Continuity. This is all about translating real-world word problems into math. Let's break down this classic drone and ship problem. A drone flies horizontally at 80 kilometers per hour at a constant 4-kilometer height, chasing a ship that's moving away at 5 kilometers per hour. We want to find the distance between them at the exact moment the drone is directly overhead. Now, always draw a diagram for relative velocity. The net closing speed is 80 minus 5, which gives us 75 kilometers per hour. If their initial horizontal distance is, let's say, 30 kilometers, the time to close that gap is 30 divided by 75, which is 0.4 hours or 24 minutes. At that exact moment, the horizontal gap is 0. Therefore, by Pythagoras, the straight line distance between them is solely the vertical gap, which is exactly 4 kilometers. Next up, let's look at continuity. For a piecewise function to actually be continuous, the left-hand limit must equal the right-hand limit, which must also equal the function's actual value at that specific point. Evaluating our limits here gives us 2a plus 3 on the left and 5 on the right. By smoothly equating these, 2a plus 3 equals 5, we instantly solve for a equals 1. And since f of 2 equals the right limit, b simply equals 5. Easy. Finally, Module 5, Advanced L'Hopital's Rule questions. We are tackling those heavy 9-mark infinity minus infinity, 0 to the 0, and 1 to the infinity forms. First up, the infinity minus infinity form. We have the limit as x approaches 0 of 1 over x minus 1 over sine x. Now, you cannot apply L'Hopital directly to this. We literally have to algebraically combine the fractions first to force a 0 over 0 form.
Combining them gives us sine x minus x all over x times sine x. Okay, now it's 0 over 0. We apply the derivative rule. We get cosine x minus 1 over sine x plus x cosine x. But look, it's still 0 over 0, so we differentiate a second time. We get negative sine x on top and 2 cosine x minus x sine x on the bottom. Now plugging in 0 gives us 0 over 2, which is simply 0.
Next, we've got the 0 to the power of 0 form. The limit as x approaches 0 from the right of x to the power of x. The strategic move here is using natural logarithms to pull that exponent down. Let y equal x to the power of x. Then the natural log of y equals x times the natural log of x. We rewrite this as ln x over 1 over x to force a negative infinity over infinity form. Applying L'Hopital gives us 1 over x divided by negative 1 over x squared, which simplifies beautifully down to negative x. As x approaches 0, that equals 0. But remember, that's ln y. If ln y approaches 0, then y approaches e to the 0, which is just 1.
And lastly, the 1 to the power of infinity form. The limit as x approaches infinity of 1 plus a over x, all to the power of x. Just like before, we take the natural log, giving us x, times ln of 1 plus a over x. We rewrite it as ln of 1 plus a over x divided by 1 over x, giving us our trusty 0 over 0 form. Applying L'Hopital here requires some chain rule action on top, yielding negative a over x squared divided by 1 plus a over x. The denominator's derivative is negative 1 over x squared. Look at that, the negative 1 over x squared's terms cleanly cancel out, leaving just a over 1 plus a over x. As x approaches infinity, a over x becomes 0, leaving just a. So the natural log of our limit is a, which means the limit itself is e to the power of a. And boom, that covers all 9 essential exam topics. From factorization to L'Hopital, derivative methods to partial fractions. Keep practicing these core methods, trust the steps, and let me ask you, are you finally ready to crush this exam?